Hi everyone, this is part 2 of the video lecture for class 21 of PH 125, and in this video we're going to be talking about the moment of inertia and rotational energy. So let's go ahead and get started talking about rotational kinetic energy. Remember that translational kinetic energy, K, is equal to 1/2 mv squared. And so now we want to know what is the kinetic energy associated with a rotating body, because kinetic energy is just the energy associated with motion. All right, and so to answer this question, we remember that omega is going to be the same for all objects on a rotating body, or it's going to be the same for all points on a rotating body. However, remember that V is equal to R times omega. So that means that points at different distances from the axis of rotation will have different translational speeds V, which is what we're thinking about when we think about our translational kinetic energy, 1/2 mv squared. All right, and so then we want to think about how could we calculate the rotational kinetic energy when we know that the different objects at different points on a particular rotating body could have different speed v because they're at different r locations. Okay, so to do this, we're going to start with a simple example, which is a point mass in uniform circular motion. In other words, this is just a little tiny dot of mass, so it's very concentrated, it's a small point of mass, and it's moving on a circular path with constant speed v, and the radius of the circular path is r. Okay, so if we were to think about the kinetic energy of that particular point mass, then we could just go ahead and use this kinetic energy relationship that we already know, 1/2 mv squared. And what we can do is we can plug in the fact that V is equal to R times omega. So I've done that down here. We have 1/2 m R times omega squared. All right, then what I did is I just distributed that square to both R and the omega, and then I just grouped things in a kind of different way. So I grouped together m and r squared, and I'm left with 1/2 mr squared in parentheses multiplied by omega squared. Okay, and so then it turns out that we call this term in parentheses mr squared. We call it the moment of inertia I. And specifically, this is just going to be the moment of inertia for this particular situation where it's just one little bit of mass moving around in circular motion with constant speed v at a radius r. Okay, so if we define the moment of inertia of this point mass to be mr squared, then we can say that the rotational kinetic energy of this rotating object is equal to 1/2 I times omega squared. All right, so let's just kind of summarize here. Rotational kinetic energy of a rotating body is going to depend on the angular speed squared, so omega squared, and also the distribution or location of mass around the axis of rotation. And we quantify this with something called the moment of inertia I. Specifically for a point mass, we found that I is equal to mr squared. However, we're going to have to generalize this for other objects. So in general, things are more complicated than a point mass moving in uniform circular motion. So for example, we're going to consider this dumbbell that I have drawn in up here, which is two masses that are held together by a rigid arm. Okay, and we're going to consider this dumbbell as it rotates around a vertical axis with a rotational speed and angular speed omega. All right, so now I want to think about what is the kinetic energy, the rotational kinetic energy of this dumbbell. All right, so if we want to do that, if we want to think about a general situation where we have objects made up of a sum of masses like I have here, right? So I have two separate masses here. If I want to do that, what you want to do is you just divide this total object up, divide this dumbbell up into its individual mass elements. Okay, so our individual mass elements, we call them m sub I, where I is an integer value from 1 up to the total number of mass elements that you're dividing your object up into. So in this case, we would just have n equals 2. We just have two mass elements, or two balls on the end of the dumbbell. And so then I would say that one of them has mass m1, the other one has mass m2. So I in the first case is 1, I in the second case is 2, and then the total mass of the object is just the sum of these two masses, m1 plus m2. All right, then we could think about the distance for each of those little bits of mass, so each of those mass elements, we can think about each of their distances from the axis of rotation. So here I've drawn in R1, which is the distance from the axis of rotation to mass 1, and then I've drawn in R2, which is the distance from the axis of rotation to mass 2. And then we know that if this object is rotating with angular speed omega, then both of those masses are going to have the same angular speed, even if they have different radii from the axis of rotation. Okay, and so then we can calculate the total kinetic energy of this system, which has been broken down into different little bits of mass. So if we wanted to do that, we would just add together the kinetic energy of each of the individual mass elements that we've broken our system up into. Okay, and so then I could think about 1/2 mv squared for each of my little mass elements, and I would just add them all up. Then I'm going to use the fact that VI, which is the tangential velocity of our individual mass element, can be rewritten in terms of that individual mass element's distance from the axis of rotation and the overall angular speed of our object. All right, then I can square each of those two terms, so Ri and omega. And then inside this sum, I have a factor of 1/2 in each term in my sum. I'll also have a factor of omega squared in each term inside the sum. And so that means that I can pull those two things outside of my sum. And what I'm left with is 1/2 multiplied by the sum over all of our little bits of mass that we've broken our object up into. So those masses multiplied by their distance from the axis of rotation squared, and then we multiply that whole thing by omega squared. Okay, and so then it turns out that that term in the square brackets there is what we call the moment of inertia I. And so the total rotational kinetic energy of this object that we've broken up into little bits of mass is just going to be 1/2 I omega squared, where I then is going to be the sum of m sub I r sub I squared for each of the little bits of mass that we've broken our object up into. So let's just look at an example. I think an example helps with these. And so then we can think about, in this case, we would write down the moment of inertia is the sum of m1 times its distance from the axis of rotation squared, plus m2, our mass 2, multiplied by its distance from the axis of rotation, r2 squared. Okay, so that would be the moment of inertia for this dumbbell. And then if I wanted to calculate its rotational kinetic energy, it's just 1/2 times that moment of inertia multiplied by omega squared. All right, so this equation, it can be a little bit hard to work with. We do have some practice problems coming up, but I will just tell you that there is a key takeaway in thinking about the moment of inertia. So in general, when we think about the moment of inertia, we just want to remember that if you have more mass that's far away from the axis of rotation, you're going to end up with a bigger moment of inertia. And that comes directly from this equation. You can see the farther your mass is from the axis of rotation, the bigger your moment of inertia will be. Okay, so let's just kind of summarize this idea of the moment of inertia. So first of all, what is the moment of inertia really telling us? It's telling us how mass is distributed around some axis of rotation, and it also tells us about the resistance to the change in the rotational speed of an object. So remember, inertia is resistance to change in motion, and so specifically when we think about the moment of inertia, it's telling us about how resistive our object is to change in its rotational speed. So if you have a larger moment of inertia, larger I, you're going to have more resistance to change in rotational speed. All right, and like I mentioned on the last slide, the more mass you have farther away from the axis of rotation, the larger I you're going to have, or in other words, the larger resistance to change in rotational speed you will end up with. So then we also learned on the last slide that if you have objects with a finite number of masses, or if you can take your object and easily break it up into little discrete bits of mass, then we can calculate the moment of inertia using the sum of all the little bits of mass multiplied by their distances from the axis of rotation squared. If instead we have continuous objects where it's harder to think about breaking our objects up into little bits of mass, then it turns out that there are well-defined relationships for the moment of inertia. So in general, they take the form I is equal to some constant multiplied by the total mass of your object m times the total radius of your object squared. So I have a few examples over here, which I will mention. You don't need to memorize these. If you specifically need one on an exam, it would be given to you. In terms of doing your homework, you are welcome to come back and reference these slides, but you do not need to memorize these. All right, last note on moment of inertia here. SI units of moment of inertia, if we just look at this formula, we have mass times radius squared, so we're going to end up with kilograms times meters squared. And then I'll just repeat this key takeaway here, which is that if you have more mass far away from the axis of rotation, you're going to have a bigger moment of inertia. Okay, so here we go. We have 4 kids, each with mass m, riding on a merry-go-round, and that merry-go-round is rotating around with an angular velocity omega equal to 3 radians per second. In the first case, case A, we have the kids near the center, so in other words, they're all a distance of 1.5 meters from the center of that merry-go-round. And in case B, they're all at a distance of 3 meters from the center of the merry-go-round. And now we want to compare the kinetic energy of the kids on the 2 rides. Okay, so there are really 2 options for solving this problem. You can do it just conceptually, or you can do it with math. So if we wanted to just think about which of these 2 objects has the greater moment of inertia, because we know that the rotational kinetic energy is equal to 1/2 times that moment of inertia times the angular velocity squared. Here they both have the same angular velocity. 1/2 is just a constant, and so the bigger kinetic energy is going to be associated with the object that has the greater moment of inertia. Okay, and so here we can think about which of these has the greater moment of inertia. Well, they both have the same total mass, but in case B, the masses are further from the axis of rotation, which is at the center of the merry-go-round, than in case A. And so that means that case B is going to have a greater moment of inertia than case A, and so that means that the kinetic energy in case B is going to be bigger than the kinetic energy in case A. So that means that I would pick answer C. Okay, and so now we know how to calculate the kinetic energy for something that is just translating, so something that's just has pure translational motion. That's 1/2 mv squared. Something that is just rotating will have a kinetic energy of 1/2 I omega squared. And we can see that these 2 forms of kinetic energy, they're very similar. In both cases, it's 1/2 multiplied by some measure of inertia, so either I or m, multiplied by some measure of speed squared, so either v or omega. All right, but then what if we have something that's rolling? So if you have something that's rolling, then its total kinetic energy is going to be equal to the translational kinetic energy plus the rotational kinetic energy. So in other words, it's going to be equal to 1/2 mv squared plus 1/2 I omega squared. So something that's just spinning will only have rotational kinetic energy. Something that's just translating will only have translational kinetic energy, but anything that's rolling will have a combination of both. So then when we have an object that is rolling, we'll still be able to use conservation of energy to study the motion of that object. Here we'll just have to think about total kinetic energy in terms of translational plus rotational kinetic energy. So in these types of problems, you'll want to think to yourself, is there work done by a non-conservative force on my object? So in other words, is there friction? If there is, then we set the work done by that non-conservative force equal to the change in mechanical energy, or in other words, the change in U plus the change in K. If not, then delta K plus delta U will be 0. Okay, so then you'll want to apply the same types of problem-solving approaches that you did before, just including rotational kinetic energy now. Okay, so we're going to finish up for today with a classic problem of a rolling race. So here's the setup. We have a hoop and a cylinder. They have the same mass m and they also have the same radius r. They're rolling down a frictionless ramp and they both start from rest at a height h. Ultimately, here we want to know which of these 2 is going to reach the bottom of the ramp first, or in other words, if we were to release them both at the same time, which one would win the race? Okay, but we're going to break it down into a few steps, and so first of all, we just want to know which one has the greatest kinetic energy at the bottom of the ramp. Okay, so to answer this question, I would be thinking about conservation of mechanical energy. Here we know that we have a frictionless ramp, which means that K initial plus U initial is going to be equal to K final plus U final. Here we don't have any springs, so in terms of potential energy, we're just going to be thinking about gravitational potential energy. Ultimately, we're going to want to think about both rotational and translational kinetic energy, but here we're just thinking about the total kinetic energy K. All right, and so now we can think about both kinetic energy and potential energy of the cylinder and the hoop at the top of the ramp. So it turns out it's going to be the same for both of them because they're both starting from height h and they're both starting from rest. So that means K initial plus U initial is going to be 0 for K initial since they're starting from rest, and mgh for U initial. All right, then we know that they both have the same final height as well. They're both reaching the bottom of the ramp. So Y final is 0 for both of them, and that tells us that the final potential energy for both of them is going to be 0. So now they both have the same total initial energy. They also have the same potential energy at the bottom of the ramp, and so that means that they're going to have the same final kinetic energy at the bottom of the ramp as well. And specifically here, it's going to be mgh for both of these two objects. Okay, so I would say that the answer here is C. They have equal kinetic energy at the bottom of the ramp. Okay, now we want to start with the same setup, but we want to ask ourselves which one has the greatest translational speed when it gets to the bottom of the ramp. And I'll remind you here that we don't need to know specific formulas for moment of inertia. We just need to know that the moment of inertia for the object that has more mass farther away from the axis of rotation will be larger. Okay, so to answer this question, we're going to have to think about rotational kinetic energy and translational kinetic energy. To think about rotational kinetic energy, we're going to need to think about the moment of inertia. So here, these two objects, the cylinder and the hoop, they have the same mass and the same radius. However, the hoop has all of this empty space in the middle, whereas the cylinder has its mass uniformly distributed throughout. And so that tells me that the hoop is going to have more mass further away from its axis of rotation, which is at the center of the hoop, than the cylinder. Okay, and so that means that the moment of inertia of the hoop is going to be bigger than that of the cylinder. All right, and so then since the hoop has the bigger moment of inertia, remember the moment of inertia tells us about the resistance to spinning that object. And so here when we think about our hoop, it's going to be more resistive to start to spin. That means it's going to require more energy to get it spinning than the cylinder will. And so that means that it's going to require a greater rotational kinetic energy than the cylinder. So then when we think about what's happening at the bottom of the ramp, the rotational kinetic energy of the hoop is going to be bigger at the bottom of the ramp than the rotational kinetic energy of the cylinder. All right, then we already know from the last problem that they both have the same total final kinetic energy at the bottom of the ramp, where that total final kinetic energy is going to be the rotational kinetic energy plus the translational kinetic energy. And so then, because the hoop has the larger rotational kinetic energy, it's going to have less energy left for translation, and so it has a smaller translational kinetic energy than the cylinder. So then, since it has smaller translational kinetic energy, it's going to have a lower translational speed. Okay, and so that means that the one that has the greatest translational speed at the bottom of the ramp is going to be the cylinder. I would pick answer B. All right, so then last question here, which was our ultimate goal, which one gets to the bottom of the ramp first? Okay, so now we can just combine the information from our last two problems. The hoop, remember, has more energy that has to go into rotating it, and so that means that it has less energy left for going forward down the ramp, for translating down the ramp. So then it's going to have a lower linear or translational speed when it gets to the bottom. And since it has a lower translational speed, that means it's going to get to the bottom more slowly. So in other words, the hoop is going to lose and the cylinder is going to win the race. Answer B here. All right, that's it for today. I know it was a lot of information. We're going to do a lot of practice, and I will see you guys in class.